Okay, so chapter 13 does our simple harmonic oscillators and our simple harmonic motion. Then we're going to move into waves and discussing waves. And we're going to discuss several different types of waves, and we're going to move into it. I'm also going to introduce a little bit from later on in the semester, because we're in an accelerated semester, accelerated summer. So we're also going to talk about the other kind of waves. So we're going to go into looking at those waves. You do have a set of lecture notes on waves. So our types of waves, first of all, let's think of what we mean by a wave in physics. So if I'm on a pond or a string, I can set up a pulse. And that pulse is going to move along the string. And you've seen it. If you're in the gym and you're doing the ropes, you can get those pulses going down. Or if you say somebody do a snap, you'll see that pulse go down the string. So I actually am going to have a movement here. So we've got two types of movement. We have movement in the x direction because it's moving down the medium. And if a string would be a medium, if I hit your desk, I'm going to get a pulse that goes down in the desk. Talking is going to create a wave in the air, and we'll talk about that here in a second. But when we get this pulse. Now, most of the time we think of a standing wave, or we think of waves in the pool, or we think of something else. And so what we end up seeing is something that looks like this, which we have just seen. So we can take this wave, that simple harmonic motion, and look at it in the wave, except now I've got to account for the fact that this is moving in the x direction, not only moving in time. Now, if I look at the one little object, and you guys have a GIF in Blackboard on there, if I'm looking at my string as a series of beads, as the wave goes through, this bead is going to travel up and it's going to travel back down. It's going to stay in place as my wave goes through the area. Okay, it's going to stay in place, but this one little piece is going to move up and down. Now, depending on the tension in my rope will depend on how fast my wave travels through. Depending on whether I have wood or steel or water will depend on how fast my wave goes through. And what we're talking about in this case is we're talking about mechanical waves. Mechanical waves, like a wave in a string, a wave on a harp string, or a wave in your arrow or your bow, your wave in a guitar string. And that's why, think about your guitar strings. And my guitar strings, I've got 6 different strings here, and they have different thicknesses. If I'm using the G or the A, it's going to have a different thickness. If I look into my piano, I'm going to have some strings that look like fishing line and some strings that look like coiled copper wire. And that thickness is going to allow for how fast that we're going to get that. And we'll ultimately talk about, when we talk about sound, we'll talk about standing waves, because that thickness and how things move fast through the wave will make a difference. Now, the reason I bring that up, even though not one of you talked about it in your introductions, is how does sonography work? When I'm doing a sonogram, I am putting a sound wave through a person's body, but sound is going to travel through my bones differently than it's going to travel through soft tissue. My liver tissue, sound is going to travel through differently in my liver than it would, say, in my kidney. So we're going to see that different transmission of sound. We're going to see a different wavelength, and we're going to get the reflection of that wave back a little differently because of how that sound wave is going through. So that pulse and that idea of looking at the speed of the wave based on the tension, or based on the complexity of my material does make a difference. You have a couple of homework problems that are related to it, but typically I don't test over the speed of wave in a string. I want you to know about it. I want you to look at it, and because it's important in sonography, it's important as we start going into other things, but it's not necessarily working those problems isn't the be all to end all. I want you to work the problems on velocity and acceleration a little bit more. I want you to understand that sound is going to move through, or the wave is going to move through. And this idea of a mechanical wave is different from other waves that we're going to talk about. Mechanical waves require a medium. And what we mean by a medium is water, string, wood, metal, air, argon gas. We've got to have sound. Those waves are going to have a medium, because it doesn't matter what type of wave you have. All waves transport energy. And it doesn't matter whether I've got a mechanical wave or an electromagnetic wave, it's going to transmit energy. And we know that. That's, we've seen a percussion grenade. We've heard if you've been close to lightning and you've heard that thunder boom, you feel it. If I stand next to a speaker, you can feel it. Those waves that are coming at us, they are transmitting energy. The other wave, as I've mentioned, is the electromagnetic. And we're going to come back to that towards the end of the semester, but I do want to introduce, it's a type of wave. Want to introduce it now because you know that we've got waves and there's a lot of commonalities between electromagnetic waves and mechanical waves in terms of how we define frequency, how we define wavelength, how we define velocity. All of those things come together, but it doesn't matter whether I have an electromagnetic wave or a mechanical wave. It's just that those things are common, but mechanical waves require mediums. And that's what we're going to be working with for the rest of this week and next week, because we're going to be dealing with sound waves. We're going to be dealing with those mechanical waves. There are also two types of waves, and it doesn't matter whether they're electromagnetic or mechanical or what. We have a wave that looks like this, and in fact, I've got a picture of those waves. I have a picture. A slinky is the best way to describe these. All right, slinky is absolutely the best way to describe them, because I can get both types of waves with the slinky. I can make the slinky go up and down, and this is a transverse wave. So I think one of you asked, am I going to ask conceptual questions? One of the conceptual questions I will ask is describe a transverse wave and describe a longitudinal wave, and what's the same and what's the difference. Now, this transverse wave goes up and down, and you can see the nice sinusoidal pattern. You can see that. My longitudinal wave, which is what our sound waves are going to be, and we talk about sound and going into sound, those are going to be compressed, stretched, compressed, stretched. And you can see a pulse down a slinky. You can actually watch that pulse move, and you can see the little springs change up and back. Well, why that's important for a sound wave is because this is what a sound wave is going to look like. There's my compressed, my rarefication. That's the big word of the day. That's your quarter word for today. Rarefication. There's my compressed, my stretch, my compressed, my stretch, my compressed, my stretch. And there it goes. And I can still represent it as a sinusoidal pattern, just like I can represent my transverse wave as a sinusoidal pattern. So these things become very important as we are going to be able to use our description. Now, whether I've got a mechanical wave or I have an electromagnetic wave, the velocity of my wave is going to equal the frequency times the wavelength. frequency times the wavelength. So if I'm drawing my wave, this is my wavelength. The distance for one complete wave from point to point. You can measure it any place you want to, but you're making one complete cycle of the wave. That is your wavelength. The time that it takes to go here is the period, and remember that the period is equal to 1 over the frequency, or the frequency is equal to 1 over the period. So if my wavelength is in meters and my frequency is in 1 over seconds, my velocity is in meters per second. So we can calculate wavelengths. In your homework problems, when we're dealing with like guitar strings and harp strings, you can calculate this velocity based on the tension in your string. But it doesn't matter where we're dealing with my wavelength and my velocity. I'm going to get that for these. And this equation holds for mechanical and electromagnetic waves. We want to cover one other idea. So if I have my pulse going through and it hits a wall, it's going to reflect. So it's going to come back and look like this. So if it's traveling this way, and if I've got an end here, it's going to go back that way. So we look at reflection, how a wave bounces off of an object. Now that becomes important because we want to explain noise canceling headphones. We want to explain why, if I have, and everybody's seen this picture, right? I dropped 2 pebbles into the lake. And we see these patterns where I can get what we call constructive and destructive interference. I think I spelled it right. I can get constructive and destructive interference because I can add waves. So let's say I have a little wave and a big wave. And this little wave is moving faster than the big wave. As the little wave comes in, I might get a bump on my big wave. And then I might get a bigger wave. And then I'll see as the little wave travels through it, it bumps out and it goes on. And that little wave passed through the big wave, and we saw that change move forward. We saw that change goes forward. If I did something that looked like this, and we did the same thing, as the little wave comes in and interacts with the bigger wave, I might get something that looks like that. And then I might end up with my bigger wave and my little wave going like this. Well, that one's still going that way, and this one's going that way. So we can get constructive and destructive interference, and our waves will add. It's called the superposition principle. We can add those things. And this is going to become important a lot of different reasons. Noise canceling headphones, how we can use our rooms to build up resonance, how we can cancel that sound out. All of that constructive and destructive interference really works towards our programs there. All right, you do have a set of notes on this one. You've got your key wave equations, you got reflections in the string, you've got a few of things there. You know that I'll ask a question about transverse and longitudinal waves, and I will open this one up for questions.